we're going to be given a vector of points as xy pairs, and we are going to compute the area inscribed by this polygon. We're going to use something called the shoelace formula, which briefly described says that the area is half the absolute value of the difference between the sums of the diagonal products and the antidiagonal products. This might sound like a lot of steps, but we'll take it one at a time. Here are some sample points. The first thing that is specified in the instructions is to stack them on top of each other to become a matrix. Here's a little lambda for that. And this is the mix function. It's called mix because the points here are given as an one-dimensional array of one-dimensional arrays. The inner dimension is hidden inside the array. Mix mixes together the outer dimension and the inner dimension into a two-dimensional array. That is a matrix. Omega refers to the argument. So here's our matrix. Now, there is a slight problem that we can also be given just a single point, which isn't a list of lists, it's just a simple list. So we need to normalize the input a bit. We can see here that it might look like we have a table, but if we ask for its shape, then the shape is just 2, it has 2 elements, whereas if we ask for the shape of the mixing of this list of points, then the shape has 2 elements, the number of rows and number of columns. So we need to normalize, and the best way to do that in a case like this is to use the enclose if simple function, or a nest function, guarantees that the result is nested if at all possible. So here, this becomes a single element of 2 elements, and then we ravel that, straighten it into a list of such pairs. Now we have a 1-element list of this pair, and then we do the mix, and then we get a 1-row, 2-column matrix, which looks much the same as before. The trick here is that if we use our list of points, then this function doesn't do anything, because it only encloses if the argument doesn't already have enclosures, and since we already have a vector, then raveling into a vector doesn't do anything either. So this takes care of the normalization. Now, the next step is we want to get the diagonals. We want 2 paired up with -8, 3 paired up with 2, and 1 paired up with 4. APL works very much orthogonally with arrays. Rows, columns, layers, not along diagonals. The easiest way to get to the diagonal is to rotate things, to skew the array into place such that what was previously diagonal is now straight. If we could only rotate up this column one step with the 4 cycling around to the bottom, coming in next to the 1, then we have achieved straightening out the diagonals into horizontal rows. Good thing is that we have a rotation function, which can either take a single value to rotate the entire array. Here we took the row containing 2, 4 and rotated it down to the bottom, or we can give it one number per column. We want the first column to be rotated 0 steps and the second column 1 step. And now we have the diagonals as rows. We also want the antidiagonals, and we could just do that by rotating the other direction with a negative number. Now we have 2 paired up with 2. If you look at our original array up here, 2 with 2, and we've got 3 with 4, so that's diagonal in the other direction, and so on. Right, that means we can take these two formulas here and put them next to each other, giving us a 2-element vector of these rotated matrices. You'll see that there's some code duplication going on here. This normalization and making into a matrix, we're doing that twice. We really should move that out of our function as a kind of preprocessing. In order for this to become a proper function in the end, we need to bind together these functions here. So it's a sequence doing this after doing this after doing this. We can do that using the top operator, and it looks cute too. Okay. The next step is that we want the products of these diagonals pairs, which are now just rows. So we can use a multiplication reduction horizontally, and that gives us these three products. So negative 16 is 2 times negative 8. Then we need to sum them. And then finally, we have to subtract one from the other. Once we have this number, we just need to take the absolute value. It's negative here, so make it positive, because the area is always positive. And then we have to divide that by 2. I like to write that 2 divides. So this operator here takes the division symbol and flips its arguments so that what we're dividing by goes on the left. And that gives us 7, which is our correct result. This is a solution, but it bothers me that we have some duplication here. We can see the sum of the product, and it really shouldn't be that we repeat ourselves. What's going on here is that we have subtraction, but we want to pre-process both arguments to the subtraction by doing a product and then doing a sum. So we have something called over, which is a preprocess both arguments operator. It takes a function here on the right, which is something we're going to apply to both arguments before we proceed to the main function, which is on the left. So we want the sum of the products. That means we can remove those over here. Right? We still get 7. But I'm not quite satisfied yet, because we still have some duplication here. All of this is really the same too. We're just talking about the difference in the two arguments are just the rotation amounts. So we could put things together here and say that the arguments are just the rotation amounts, and they will be used to rotate the actual argument to our function as a whole. How do we do this? Well, let's put the argument name in here and a rotation function. Now we want to bind together this argument as a constant argument to the function. So instead of this being a dyadic function, takes an argument on the left, the rotation amount, and an argument on the right, what's being rotated, it now becomes a monadic function that's being applied to each argument. It is a rotate omega function. So that means we can get rid of these two. A slight hiccup here is that this is a tacit function that we're using, and that's necessary because we want to refer to the argument of the outer function. If we used braces here to make a little lambda, then omega would now mean the argument that's being given to this over construct. So being that it's tacit, we can't just have 3 monadic functions after each other. That would mean something else. But we can, the same way we did over here with the preprocessing, we can glue together these two with this top operator. This is looking better. Now we're just giving the rotation amounts as arguments. But can we go one step further? Yeah, I believe we can, because we're not actually interested in not needing to rotate the first column. The only thing that's important here is rotating the second column. So how can we get rid of that 0 there? Let's restructure what we have got in here a little bit. We have the amount being inserted here on the left with what's being rotated on the right. We can, instead of having it the whole thing as a compound function, the product of the rotation on omega, we're going to make this into a fork construct instead, where the right argument goes over here. We have a central function that is applied to the result of fetching the right argument and this constant on the right. Problem is that in a tacit context, we can't have an actual constant on the right. It has to be a function on the right. So we'll use this operator again, but now with an array on the left. It doesn't flip around arguments. Rather, it changes this constant into a constant function. So this returns the other argument, and this is the rotation amount with a post-processing of a multiplication, and this refers to the arguments giving to the whole over construct, which is going to be -1 on the right and 1 on the left. We don't want just that 1 or -1. We want the concatenation of 0 and that 1 or -1. So that is 0 and concatenation, and just the same way as we did before, using the bind operator to bind a right argument to the rotation function, we're now going to use that same binding operator to bind a left argument to the concatenation. So we're going to evaluate this constant function that gives us the outer argument. We're going to apply the 0 concatenated to function to -1 first, and then we're going to use the result of that as rotation amount for the vertical rotation, post-process using the multiplication, and then we sum up. And then afterwards we're going to do that with a 1 instead of -1. And then we do the final subtraction. So this is about as compact and non-repetitive as I can put it. We can give it a name and apply it to the points or to a single point when the area then is 0. Thank you for watching.